Madam, good evening.
Good evening. Just a minute. We'll just wait for one more minute and then we'll start. Okay, so anyway, it's already 8 minutes past 6, so we'll start. And if somebody is joining, they can join while we continue the session. So I'll share the screen.
Okay, ma'am.
And one more thing, I'm seeing this scheduled sign in Google Meet right now, so which means I think the meeting might end in an hour. So before it ends, I will create another link and I'll put it in the chat so that you can rejoin once that is done. Okay, so yeah. So, welcome to yet another problem solving session for the course Geographic Information Systems. The instructor is Professor A.K. Saraf from IIT Roorkee, and I'm Anshana, teaching assistant from IIT Kanpur. So, today we'll be primarily focusing on the week 10 lectures, but at the same time, during the problem solving, I'll also include the assignment problems of week 9 since the solutions are already out, so that it'll be kind of like a revision for you. So in this session, we'll start with the aspect calculation. So I've just picked certain topics that I feel needs to be discussed, and it is a little like you have a lot of topics discussed in week 10. So I've not completely included that. The remaining I'll be including in the next session. So yeah, anyway, so for aspect calculation, so what is exactly the aspect? It identifies the downslope direction of the maximum rate of change in value from each cell to its neighbors. Like basically, it talks about the direction of the slope. And in terms of these cells that we talk about, just let me connect the pen, that notepad with this so that I can draw and show you. Okay, so yeah, as I was saying, aspect basically talks about the direction of slope, and here what they are saying is it identifies the downslope direction of the maximum rate of change in value from each cell to its neighbors. So that is like you have a grid. By now you're quite familiar with this representation. So you have these grids available, right? And each grid will have some sort of values define telling you about what kind of slope is there or something like that, right? Or slope aspect, like you have grids telling you about slope, grids telling you about aspect. So basically here aspect will identify the downslope direction of the maximum rate of change. For example, let's say here it is 5. This is a random number that I'm giving, and then probably over here you have a 10. So that's like a very, and here it might be just a 4 or something. So a maximum change is shown in this part, right? So that is what aspect sort of takes into consideration. Now this is measured clockwise because it's a direction. So it is measured clockwise in degrees from 0 to 360. Like 0 degree north, that is what they've written here as due north. Okay. So 0 degree north to 360 degree north, which is basically just 0 degree, but then it has covered 360 degree. Okay, that is what this diagram is also showing you here. Like first we have a 0, then 90, 180, 270, and again if you add a 90, what will it be? It will be 360, right? So 0 and 360 are more or less same, but then like it sort of tells you that it has completed one complete circle kind of thing. Okay, so that is how aspect is measured. It is measured in terms of 0 degrees to 360 degrees. So it can be anywhere in between this. And wherever you have flat areas, like where you don't have any downslope direction, there you give the value as -1. Other than that, in all the other cases, we will be talking about this in terms of 0 to 360 degree. Now here you can see also, this is like elevation raster. So this is just talking about how high certain parameter is. And here you can see as it gets more this brown dark color or this thing. So here from this itself you can understand, right? Here it is an hill kind of thing. Here you have a hill. Here you have a hill, and here these are like sort of low-lying areas, probably valleys. Okay, so that is what you understand from this diagram. Now in aspect raster, it also talks about the direction. That is what it is here. Like this gray color, I can't see that properly in this diagram, but wherever that gray color is there, that is the flat area, which is like basically you don't have any downslope direction. So that is -1. Then when you see other direction, like if it is north, which is right, that means it is like 90 degree. I mean, not 90, sorry. It is 0 degree, or it can be even 360 degree. Okay. Then northeast means 45 degree. Okay. Then east means 90 degree. So like that, like we just, according to this here, I think this is northwest. So northwest means what? 315, right? So accordingly, we have just changed this input elevation raster into an output. Like this is the input, which is an elevation raster, and the output is a aspect raster. Okay, so that is what is shown here. Now here we have an aspect algorithm. So here I'm discussing about that, like it's coming in the upcoming slides also. So I thought it's better to talk about it here. So it's basically a moving 3x3 window which visits each cell in the input raster, and for each cell in the center of the window, an aspect value is calculated using an algorithm that incorporates the values of the cell's 8 neighbors. So like it's a big definition, but what you just have to keep in mind is that it is a 3x3 window. What is a 3x3 window? You can see there are 3 cells in this direction, 3 cells in this direction. So this is a 3x3 window. Now what does it do when you are doing this calculation? So what happens is, let's say you have a very big grid, okay? I'm not drawing everything, but just assume that this is a very big grid with so many small cells, okay? So what it essentially does is, it will just first pick a 3x3 window. So in this big grid itself, it will choose a 3x3 part like this, and then it will calculate the aspect. So how does it calculate? An aspect value is calculated using an algorithm that incorporates the values of the cells of 8 neighbors. So what happens is kind of like the spatial interpolation that you do. So in spatial interpolation, how was it done? Like you basically had one point based on which you determine the values for the surrounding region, right? But instead, here what are we doing? Like we are considering this E, uh, like we are like that is the point that we are considering. And what do we do? Like this, all these 8 cells that is surrounding E, that is A, B, C, like 1, 2, 3, 4, 5, 6, 7, 8, 8 cells. So that is what they're saying. This 8 neighbors, whatever value is there, we will based on some algorithm, we will calculate, and that value will be assigned to the center point. So the cells are identified as letters A to I, with E representing the cell for which the aspect is being calculated. So the aspect will be calculated for E. Okay, so that is how we sort of determine the aspect for each of this uh, what do you say, like a very big grid that you have. So that's how you calculate it. So in case of this aspect algorithm, what does it do? That is like basically taking the rate of change in both the x and y direction for cell E. Aspect is calculated using. So what it does is, in both the directions, like in this direction also, it sees how it is varying, the aspect is varying, and how it is varying in the downward direction. So both in x and y direction it will see, and then it will make use of this formula for calculating the aspect. Some kind of like change in that rate of change is what is shown here, dz by dy minus dz by dx. That is basically the third one, like x, y, z that you have, horizontal, vertical, and then the like this is sort of like the three-dimensional aspect. Okay, so the aspect value is then converted to compass direction. So from this you get some value. Now that value will then be converted to the compass direction values, that is from 0 to 360. That needs to be done because aspect is represented in terms of 0 to 360, right? So the aspect value will get converted to the compass direction by following this rule. Like they just put it like this, that if the aspect is less than 0, then you need to uh, give this value for the cell. If the aspect is greater than 90, you need to give this, like calculate that value like this. Or if the cell is equal, like if it is anything other than these two, that is if it is not less than 0 or not greater than 90, something else, then you do this. Okay, so this is kind of like you're giving some conditions. Okay, and why are we doing this? Because the aspect that you calculate initially by using this equation will not give it in the terms of 0 to 360 degrees or in the compass direction value. So you need to convert it into the compass direction value based on this logic. Okay, this is the rule that is being followed. Now there are basically two methods in which you can compute the aspect. Okay, and they are, first one is the planar method and second one is the geodesic method. Now in planar method it is basically a two-dimensional method, okay, and geodesic is a three-dimensional method. So this is, I think, probably from ArcGIS. So planar is the calculation will be performed on a projected flat plane using a 2D Cartesian coordinate system. And the geodesic one is the calculation will be performed in a 3D Cartesian coordinate system by considering the shape of Earth as an ellipsoid. Okay, so here it is in done in a Cartesian coordinate system, and here it is done in a 2D Cartesian, and here it is done in a 3D Cartesian coordinate system. So now we'll just go through what each of this means, like what is the planar aspect computation and what is the geodesic aspect computation. So in case of the planar method, it is the traditional method that is being used, because like obviously like the 3D thing that all came on later, right? So the traditional way was the planar method for calculating aspect. So again, what I said, a moving 3 by 3 window visits each cell in the input raster, and for each cell in the center of the window, an aspect value is calculated using an algorithm that incorporates the values of the cell's 8 neighbors. Same thing that I had shown just before. So that is the traditional method. So you have 1, 2, 3. So you have A, B, C, D, E, F, G, H, I. So we are considering calculating the aspect for E. based on an algorithm which sort of takes into account the values of the remaining 8 cells. This is the planar method. Okay. The same thing. The cells are identified from A to I, and E represents the cell for which the aspect is being calculated. So in case of this planar method, the rate of change in the x direction for cell E is calculated with the following algorithm. So as I said, it was like you have this grid, right? The 3 by 3 window. So, and you have E over here, right? Now that rate of change needs to be determined in the x and y direction, right? Because it is 2D. So in x direction, it is determined based on this equation. This is the rate of change. That is why it is dz by dx. Okay. So dz by dx is given by this equation where WGST1 and weight 2, that is like weight, I think, yeah, horizontal weighted counts of valid cells. Okay, if any sort of, I don't know, like I've not seen any calculations in your assignment, but if it comes, this is the formula that needs to be used. But I don't think such heavy calculations will be given. But just for your understanding, first the rate of change will be determined in the x direction for the cell E. Then yeah, they've also given an example. Like if C, F and I all have valid values. Okay, valid values in the sense like there is no flat, something like that. Then weight 1 will be 1 plus 2 into 1 plus 1. Yeah, for this is 1 plus 2 into 1 plus 1. If I is no data, and no data means basically you don't have anything there, right? So in that case it will be 0. If f is no data, then this value will be 2. So this here you have 4 when all the values are valid, and if like I is not, then it is 3, and if f is not like a no data value, then it is 2. So similar logic applies to weight 2, except the neighbor locations are A, D and G. So here A, B, C, D, E, F, G, H, I. Okay. So for this we have considered C, F, I for weight 1 and A, D, G for weight 2. Okay. Then the rate of change, like first you determine the rate of change in the x direction. Now we will determine the rate of change in the y direction. Like this is just to understand how the planar method is implemented. I'm not sure like it will be given to calculate manually, but then you need to understand how it is done, right? So that's why. So here dz by dy is calculated in this manner. G plus 2h plus I multiplied by 4 by weight 3 minus A plus 2B plus C multiplied by 4 by weight 4 whole divided by 8. So weight 3 and weight 4 are the same concepts as in dz by dx computation. Taking the rate of change in both the x and y direction for cell E, aspect is calculated using the following formula, which was like the one that I showed you before, right? So first and foremost, you need to determine the rate of change along the x direction. Then you need to determine the rate of change along the y direction, and then whatever values you are getting out of that you will put in this equation that is given here for aspect. From that you will get the aspect for a particular cell. In this particular case, that cell is E. Okay.
That value is automatically coming, that aspect value 57.29578.
I think that is a normalizing kind of value. Even I'm also not very sure, because in certain equations we have that, right?
Yes, ma'am.
Because I don't know, I'm not very sure how it has been derived, but that is the like equation that is given to calculate the aspect. So I think that
Yes.
could be a normalizing value.
Yeah. Last slides, I want to once again repeat it, that previous slides,
Yeah.
planning method. Yes. Once again explain it, that I want to understand once again.
Okay, this
So,
one.
yes, ma'am.
Yeah, okay, sure. So I'll just tell you, like, basically what we are doing in planar method is like we have this 3 by 3 window, right? So in 3 by 3 window, we have 9 cells completely, but we are actually calculating the aspect for the center cell, which is over here, which is E, because that is how we are naming it. Now what we do is that we have to calculate the aspect. An aspect is calculated by identifying the rate of change in both the x direction and the y direction in case of the planar method, because this is done in a two-dimensional system, right? So we will be considering the change along x direction and the change along the y direction. So here what we have to do, like if you're asked to calculate the aspect for a particular cell by using the planar method, then the first thing that you have to do is calculate the rate of change in the x direction for that cell. Then after once you get that value, you need to calculate the change of rate of change in the y direction. So here the rate of change in the x direction is calculated by this. The rate of change is basically dz by dx. Okay, so we have the x, y and z, right? So in order to determine the rate of change, we need to do the dz by dx. Now that this is again a formula that is being given. I don't know how it is derived. Maybe I like sir has also not mentioned it. So anyway, like however it is, this is the formula that needs to be used in order to determine dz by dx, right? So here we have this c plus 2f plus I multiplied by 4 divided by weight 1 minus a plus 2d plus g multiplied by 4 by weight 2 whole divided by 8. Now here this weight 1 and weight 2 are the horizontal weighted counts of valid cells. Okay, so this is basically, for example, in case of weight 1, you can see we are considering the C, F and I cells. Okay, C, F and I in this one is what we are considering for weight 1, and for weight 2 we are considering A, D and G. Okay, so you can see that in the formula also, where you have weight 1, we are considering CFI, the values of C, F and I cells, and for weight 2, we will be considering the values for A, D and G. Now this is like a rate of change, right? So that's why like we have to probably integrate it and find the value. Anyway, that sort of example is not shown here. But anyway, like if you have the values for C, F and I given as probably 1 valid values, which is like 1, and invalid or no data value is given as 0. So if all three are valid, we will put that value there. So you have this formula C plus 2F plus I. So C plus 2F plus I will be what? It will be like if all are valid, it will be 1, 1, 1. So like 1 plus 2 plus 1, which is 4. Similarly, if for example, let's say I is no data or F is no data, wherever that no data comes, this value is going to be 0. So accordingly, this value will change. Similarly, for weight 2 also we can do this, but here in case of weight 2, we will be considering the ADG and ADG cells instead of CFI. I don't think you will be asked to calculate this, because this includes certain like mathematics regarding the differentiation and the integration. And I've not seen sir using that, so probably you may not be asked to calculate it. I've not seen that
Yes,
in the
ma'am. Actually,
assignment.
I want to understand what the actually that happen that ADE. So why
Uh,
we are taking two app? This is
which one?
C app I. Yeah, this is the formula I think. So
Yeah.
we are taking C, but here we are taking two app. Why we are taking two app plus I? That's my
Oh,
question.
you are asking about the equation.
Yes, yes,
That,
ma'am.
but I need to know the derivation also. Here, that derivation is not given.
Yeah.
Probably, I think, like normally, I think when you are doing the integration, when you have f square, that on differentiation it becomes 2f. Like as far as I remember, I'm not very sure about that.
Okay,
Probably that's.
just ma'am for conceptual clarity only.
Yeah, okay, okay. Like that,
Okay,
the
okay.
problem is that only this equation is given, right? So I don't know how
Yes,
they have derived it here.
yes, ma'am. Thank
So
you,
that,
thank
that
you.
is the
I
problem. Yeah,
understand. Yeah.
yeah. Okay, so the aspect value, yeah. So as I said, we determine the rate of change in the x direction, then we determine the rate of change in the y direction, and then what we do is we calculate the aspect. But you, as I said, the aspect that you calculate using this particular formula is not going to give you a value in terms of 0 to 360 degree, which is the compass direction value. You're not going to get that. So in order to do that, we will use this logic. Okay, so the aspect value gets converted to the compass direction value, where we are using this logic that if the aspect value that you got is less than 0, then the cell will have a value of 90 minus whatever that aspect value is. If the aspect value is greater than 90, the cell value will be 360 minus that particular value plus 90. And if it is none of these cases, like something else, then the cell value will be 90 minus the aspect. This is a logic that they're putting in order to find the value for what? E. This is what we have been trying to do since the beginning. Like we need to find a value for E. So for that we are considering the change along the x and y direction. Then we find the like whatever that change value you are getting, we put that in the aspect equation, and then you get a value. But that value is not valid as long as you don't get it in a not, I'm not saying invalid, but then you can only use it when you do convert it into a compass direction value, which is 0 to 360 degree. This is something that you can keep in mind. Aspect value will always be represented in terms of compass direction value. So because of that, what we do, like we give this particular logic that if aspect is 0, like less than 0, a particular cell will have the value based on this particular equation that is given here. If the aspect is greater than 90, then you have to make use of this equation. Else you have to make use of this equation. Like this is something that you are telling the the software to do, so that you give this, and then accordingly it will be calculated for all the cells. Because it, see, for just this 9 cell uh, grid, it is easier for us to calculate it manually. But if you have a very big grid, let's say maybe a 12 by 12, or not just 12 by 12, like something which is very big, okay, you have an image of a very large area, and the number of cells are also very high, it is not possible for us to calculate it manually one by one. So then what happens, like you know we'll input this particular logic, we'll calculate, we'll give this particular logic, and then it will be automatically done for the entire grid. So here we have this planar method aspect calculation example. So you can see here the planar aspect. Maybe from this you might be able to understand it a little bit. Of course, I don't have the answer for how this equation came, but then at least we can understand how it is calculated. Since that example is given, then I think it would be better that you remember this equation also, because if at all they ask you for the evaluation, then it's easier for you. So here we can see we have a 3 by 3 cell like grid, right? So here what are we doing? We'll just name it A, B, C, D, E, F, G, H and I. Okay. So this is an aspect example input. This is the input. Our output will be different. So in input, what we are first trying to do, we are trying to determine the rate of change along the x direction for the cell E, for this particular cell. Okay. So here our C is basically what? 85. Okay, so we wrote 85. 2 into F. F is 85. So 2 into 85 is 170. So here we got 170. So 85 plus 170 plus I. I is what? 84. So 84 multiplied by 4 divided by what is the formula for weight 1? That is C plus 2F plus I. Right? So that is 1 plus 2 plus 1. This weighted one, we don't actually use this value as such. What you have to remember is, 1 second, I can just write it. I'll just write it here, that would be better. Weight 1 is equal to C plus 2F plus I. But unlike how we have added, included this value which is already given in the aspect input, like for C we had written it as 85, F was again 85 and I was again 84, right? But when you do this weight 1 is what? Basically it is the horizontal weighted counts of valid cells, like number of valid cells basically. Okay, so here definitely the C cell has a valid value 85. There is nothing like it's like some data is there, right? So it has some valid value. So because of that, C will become 1, F will become 1, I will become 1. So effectively it is 1 plus 2 plus 1, which is again 4. Okay. Similarly here also we are doing the same thing. In the first part, that is over here, we are basically writing the same value that is given in the cells. So A is 101, D is 101 multiplied by 2, which is basically 202, and G is again 101. But when you write for weight 2, it is A plus 2D plus G. And there for A, D and G, we are giving the value 1 because all that cell A, D and G has what? Valid values. So for valid values, we give the value as 1. I hope that is clear. That is how we are actually calculating dz by dx over here.
Yes, ma'am.
Yeah. Similarly, for rate of change in y direction, same thing. Like here, G, H and I is weight 3 and A, B, C is weight 4. So same thing, like we put the direct values over here, then we put the weighted values and then we get a value for dz by dy. So we have a value for dz by dx, we have a value for dz by dy. Now all that you have to do is put that into this equation that you already saw, right? Aspect is equal to this thing. So here 57.29578 multiplied by A tan square, I think. Yeah, A tan square and this value. So when you calculate that, we are getting minus 2.64. Now if you remember, we had several logics, right? If the aspect is greater than 0, less than 0, those things. So here you can see the calculated value is less than 0. So the final rule that you apply here is 90 minus the aspect. If had it been more than 90 or something, then the formula would be different for calculating the cell value. But here since it is less than 0, we are using this formula 90 minus the aspect value, which is 92.64. So the value of 92.64 for the center cell E indicates that its aspect is in the easterly direction. Why? Because 92.64 is what? In terms of compass direction, and that is, if you remember, this is how north, east, south, west, and this is 90. So 92 might be definitely slightly more than this, but then that will be in the east direction. So you can understand that the center cell is in the easterly direction. So based on that, we'll get, and then the remaining will be calculated according to that, and then we get something like this. So this was the input, and this is the planar aspect output that we got. So here, just like how it was shown in the previous one or two slides, it was shown that if it is a flat region, the value is given as -1, and then based on all these things, like if it is in not like 0 to 22.5, that is north, 22.5 to 67.5 is northeast, then 67 to 112, because see, although we say north is 0 degree, east is 90 degree, but that's not exactly how we can classify, right? So we give a range of value. So 0 to 22.5 can be considered to be in the northerly direction, and then 22.5 to 67.5 in the northeast, 67 to 112 in the east, like that. Okay, so it's like you have to consider a range of values because it's not so very specific in the real scenario. So that is regarding the planar method. Then we have the geodesic method. So the geodesic method, it measures the surface aspect in a geocentric 3D coordinate system. So that 3D coordinate system is also called the Earth-centered Earth fixed coordinate system, which is also written as ECEF, by considering the shape of Earth as an ellipsoid. So by now you have to understand that although like in our globe is like a sphere and all those things, but in a realistic representation of the earth would be like an ellipsoid. So it's not so uniform, it's slightly elongated along the equator. Okay, so here in geodesic method we make use of the geocentric 3D coordinate system known as the earth centered earth fixed coordinate system, and we consider the earth's shape to be that of an ellipsoid. In this case, we will use the Z units, that is the height units of the input raster if they are defined in the spatial reference. The geodesic method produces a more accurate aspect than the planar method. The thing is, planar method more or less makes use of the XY direction, right? Because it is 2D. But in the geodesic method, it also takes into account the variation along the third direction. So that is a little more accurate. So even though we say the planar method is the traditional one, the more accurate one is the geodesic method. So the Earth-centered Earth fixed coordinate system, it is a 3D right-handed Cartesian coordinate system with the center of the Earth as the origin, where any location is represented by XYZ coordinates. So here you have to imagine that whatever is shown here, just a minute. Okay, so here what is shown here, you have to imagine this to be the ellipsoid that is representing the earth. Okay, so it's slightly elongated along the equator, and this particular circle that is sort of representing the equator, which is 0 degree latitude. Now what they're saying is, in the earth centered earth fixed coordinate system, the center of the earth is regarded as the origin, that is the point 0. Okay, and any location can be represented in terms of XYZ coordinates, because see, it's a ellipsoid, it's a three-dimensional structure, so you will have X, Y and Z coordinates. So for example, this T, that is a target location over here on the surface. So what do? You just make a from the origin how far it is. So you have the x value for that, that is x, this is the xt z, sort of like this, something like this. Okay, this is x, y and z. So that for this particular point, you will have the xt, yt and zt. The phi that is shown here, that indicates the latitude. The lambda indicates I don't think you have to go into that much detail. You just have to remember that in the ECF coordinate system, any point on the surface of the earth will have a x, y and z coordinate. And you just have to remember that in geodesic method, the assumption is that the earth is in the shape of an ellipsoid. So the geodesic computation uses an XYZ coordinate that is calculated based on its geodetic coordinates, that is latitude, longitude and height. Okay, based on that we will get X, Y and Z. If the coordinate system of the input surface raster is a projected coordinate system, like we had discussed before, the raster is first reprojected to a geographical coordinate system. So geographical coordinate system means in terms of latitude, longitude, those kind of things, where each location has a geodetic coordinate. Then only it is transformed into a ECEF coordinate system. So it's kind of like a process, like how you had done in case of the planar method. Like first you determine the rate of change along x direction, y direction, then you calculated aspect, but even then you had to convert it into the compass direction value, right? So similarly, it always prefers that the coordinate system is geographical, like the input coordinate system. If not, then you have to first reproject it. Then for each location, the ECF coordinate system is determined. The height, which is basically the z value, is the ellipsoid height reference to the ellipsoid surface. So this is the ellipsoid surface, like basically a realistic surface. Okay, so this is the ellipsoid surface and this is the elevation that you're showing here, this one. Okay, so the point, from the ellipsoid surface to that topographic surface, however, how much ever distance is there, that is given as h or the z value. Now this is a little more like not so straightforward like the planar method. So in order to transform the ECEF to a from a geodetic coordinate, we need to use these formulas for x, y and z. Earlier we only had to be concerned about x and y, but here you also have to consider the z part. So x, y, z, we have these equations where the n phi, so phi is latitude, right? Yeah, phi is latitude and lambda is longitude. So n phi is given by this formula. So this is like formulas are directly given. So I'm really sorry, like I don't know how it is derived. Anyway, this is how it is given. So the ellipsoid height h is in meters in the above formulas. So wherever h is shown, that is, see, always whenever we are making such calculations, you have to keep in mind that you need to know what units that measurements are given. Otherwise, it's going to be confusing, right? Because angles can be given in both uh, in different units. The height, like the distance measurement can be different, so that needs to be specified in order to understand the output that we are getting. If your input raster's z unit is specified in any other unit, it will be internally transformed to meter, because this is like a, so like you give all this information and the software does all the work. So you just have to specify that if whether that input unit is something other than meter, then the software itself will change it into the transform it into meters. So how is the aspect computed based on the geodesic method? So same thing, to calculate the aspect at each location, a 3 by 3 cell neighborhood plane is fitted around each processing cell using the least squares method. So it's sort of, again here we are making use of the 3 by 3 cell, but like 3 by 3 that grid. Here it is a neighborhood plane which is fitted around the processing cell, and they kind of like how I said, like some algorithm or something, they make into use. Here they're using the least squares method. So the best fit in the least square method minimizes the sum of the square difference between the actual z value and the fitted z value. So here that difference is being shown, okay, dz, which is the difference between the actual value and the fitted value. So that difference is what gives you the best fit. So here you can see, here is an example that I have straight away taken from the professor's slides. So the plane is represented as like each plane or line, whatever it is, they have an equation, right? So this is how the equation of the plane is. See, there are a lot of mathematics involved, uh, which I don't think we have to go into much detail. Like I've also sort of needs to refresh this. So z is the equation of the plane is z is equal to ax plus by plus c. For each cell, the dzi is the difference between the actual z value and the fitted z value. That is what we had seen in this previous diagram also. dz1, dz2. Okay. The plane is best fitted when the sum of that all that mm, that dz values is minimized. After the plane is fitted, a surface normal is calculated at the cell location. Surface normal is this one, okay? This is the point. So this is the northern direction. So from here, a perpendicular that is drawn. So that is the surface normal. So after the plane is fitted, a surface normal is calculated at the cell location. At the same location, an ellipsoid normal perpendicular to the tangent plane of the ellipsoid surface is also calculated. This is the tangent plane, this blue one. Like tangent plane is like, tangent is what? It touches the surface at one point. So that line in a planar form. So that from that tangent plane, you have an ellipsoid normal perpendicular to it. Since the tangent plane of the ellipsoid surface is considered the reference plane, the surface normal is perpendicularly projected on the plane. Finally, the geodesic aspect is calculated by measuring the angle alpha in the clockwise direction between the north and the perpendicular projection of the surface normal. See, this is the projected surface normal because this is the surface normal over here, and then you bring that onto the plane. So this is the projected surface normal. So the angle between the north and this projected surface normal measured in the clockwise direction will give you the value of the aspect in terms of the geodesic method. So in this, we are doing this in a three-dimensional manner. So here you have a surface, a tangent plane, and then you have a surface normal, an ellipsoid normal. The surface normal is like, as the name suggests, like it's on the surface, right? So that is projected onto the tangent plane, and then you determine the angle between that surface normal and the north. Then that measurement is done in the clockwise direction. Okay, it's showing that the call will end in a few minutes. So I'll create a link and I'll put it in the chat. Just a minute. Okay, so till this meeting continues, I'll continue, and then once it stops, I will start the meeting again in the other link, and we can continue with that. Then the topic that was discussed was the terrain analysis. Okay, so the analysis, these are all basically the DEM derivatives that we are discussing. So in terrain analysis, the analysis and interpretation of topographic features employing DEMS through geographic information system. So you have uh, certain topographic features for which we are using DEMS. So we need to, based on that, whatever we generated, we need to do the terrain analysis. Like we need to analyze and interpret what kind of features, how it is, like the elevation variation, the ridges, the valleys, all those things. So the such features include slope, aspect, view shed, elevation, contour lines, flow, upslope flow lines, downslope flow lines. Like several features are there, which is basically analyzed and interpreted during the terrain analysis of a topographic feature, which is represented by the DEM. The intention is to build mathematical abstraction of surface terrain to delineate or stratify landscapes and create an understanding of relationships between physical features and ecological processes. So it's not just like you are creating a model and that's it. But the basic reason why we created that model is to make certain interpretations and analysis, right? For further some purposes or something. So you can even understand the ecological processes in the area. So what we have to keep in mind is that the area of a sloping cell is not the same as one that lies flat. So as I said, whenever we are talking about these cells and grids, you have to have this picture in your mind, like something of this sort. So what they're trying to tell you is, if a cell, let's say for this cell, it's a sloping cell, like it's not flat basically. So some slope is there. So although it is represented like this, what you have to keep in mind is that the area of that cell is not the same as the one that will lie flat, because the sloped cell will require more area than the flat one. For instance, this is what they're saying, like if we walk up and down a steep terrain, we will walk far more than the planimetric length of your path. Like because you're going up and down, that area coverage is more. It's not like you're walking on a flat surface, right? So while we have known this fact for thousands of years, we are aware of that. When you actually do it, you know that it's not the same. Surface area and length calculations were practically impossible to apply to paper maps. But in paper maps, it's difficult to account for this difference in the area. But now that we have DEM, the digital elevation models in GIS, it's easier to handle such calculations and take into account the slope area, like area of the sloping cell. So in a grid-based system, planimetric area, that is like a planar area, is calculated by multiplying the number of cells defining a map feature times the area of an individual cell. What they're trying to tell you is, like, if, for example, if you have a forest cover type, okay, a particular forest cover, which is covering, which is occupying approximately 500 cells in that diagram or grid, okay, and it has a spatial resolution of 1 hectare each. What does that mean? Each cell is 1 hectare each, okay? Then the planimetric area for that cover type will be 500 cells multiplied by 1 hectare for each cell, which means the entire 500 cells is effectively covering an area of 500 hectares. So, because see, whatever DEM model that you're preparing, it's basically, you're doing that for a very huge area, right? So it's not in terms of, let's say, centimeter or millimeter. It's like in terms of meter, kilometer, hectares, whatever it is. So that's what they're trying to tell you. In a grid-based system, the planimetric area, the planar area is calculated doing this. Like if you have a particular feature type, then what you see is like first you will see how many cells uh, occupy that particular type. Then you see how much area each cell is covering. So here each cell is covering 1 hectare. So 500 into 1, you get 500 hectare. However, the actual surface area of each grid cell is dependent on its inclination. That's why it is specifically mentioned as planimetric area. Planimetric area doesn't take into account the slope. So they just directly they can multiply 500 into 1, 500 hectare. That's it. But you have to understand that the actual surface area will also have, like we also have to consider the slope, the inclination. So what happens? The surface area increases as a grid cell is tilted from a horizontal reference plane, that is the planimetric plane, to its three-dimensional position in a digital elevation surface. So here you can see that is what is shown here. Like here, this particular cell that is shown here, they have sort of enlarged it over here. So here you have a minimal surface area. That surface you can see it's a square and it doesn't occupy as much. But as you go up where that inclination is there, here the cell is somewhat like this. It's a tilted plane. And again compared to this, okay, the call is about to end. So let it end and then I'll restart. That's better. Okay, I'll wait for 1 minute and since it's a new link, let's just wait for some time and then we'll start. Okay, so I'll continue. Uh, Okay, so as I was saying, so we have this horizontal plane which has minimal surface area, and then when you go to the tilted plane, the surface area has increased. So as it is written here, surface area increases with increasing inclination. It's like slicing a stick of butter at increasing angles and noting the changes in the surface area of the patties. It's basically you can slice it horizontally, you can slice it at an angle, but in both cases the area is going to be different. That's the only idea that is being conveyed here. So surface area increases as the grid cell is tilted from a horizontal reference plane to its three-dimensional digital elevation surface. So this is a good differentiation for the planimetric versus the surface areas. So we have a DEM of a planimetric or a flat area of like 8,100 meters square. So you can see how much the area is, right? 8,100. But then in this diagram that you have on the other side, that is the black and white hill shade. So there you also take into account the inclination. Then what happens? From 8,100 meters square, the area has increased into 13,366 meters square. So the area has increased. Surface curvature at a point is the curvature of a line. Now we are talking about surface curvature. Okay. Surface area we had talked about. Now surface curvature we are talking about. So surface curvature at a point is the curvature of a line formed by the intersection of the surface with a plane with a specific orientation passing through this point. Okay. So it is basically the curvature of a line which is formed by the intersection of the surface with a plane. So you have a surface and you have a plane, and at that point of intersection of the surface and the plane, a line will be formed. So the curvature of that line will tell you the surface curvature. The value of the curvature is reciprocal of the radius of the curve. The larger the radius, the smaller the curvature value. Okay, so this in like smaller classes also we have studied the radius of curvature kind of thing. So the curvature is reciprocal to the radius of the curve. So larger radius means smaller curvature value. A gentle curve has small curvature and a tight curve has large curvature value. Okay. So the units of their curvature are radians per linear unit, the unit of the spatial reference of the raster. So it's mainly given in terms of radians because you have a curvature involved. Then we have different types of curvature: planform or plan curvature, then profile curvature, then the surface curvature kind of thing. So first we'll talk about the planform or plan curvature. There is some issue with my audio. Let me just resolve it and I'll be back in like 1 or 2 minutes. Okay, so I think it's better now. So the curvature in a horizontal plane or the curvature of the hypothetical contour line that passes through a specific cell, that is the planform or plan curvature. So here it is more or less related to the contours. Okay, so here you can see you have these contour lines, right? So this is mainly the horizontal curvature that we are talking about. So here what you can see is it measures the curvature of these contour lines, how tightly they are or how wide they are, that kind of thing. So positive, this is like plan form or plan curvature is positive for cells with concave contours. Concave contours is basically, okay, I think they gave it wrong here. Okay, this is concave, that is negative actually, and the cells with this convex one is the positive one. Okay, here there is a typo, so you have to remember the one that is bulging out, that is the convex one, and that is positive. The one that is sort of like pushed in, that is the concave or uh, negative curvature. So plan curvature can be used to differentiate between ridges and valleys. So here you can actually see that in the diagram also, right? Based on this convex and concave thing, you can actually understand where you have the ridges and where you have the valleys. So the main like application of this plan form, yeah, or plan curvature is that it can be used to differentiate between ridges and valleys. So this is perpendicular to the direction of the maximum slope. Uh, that's how you get this curvature. So a positive value indicates the surface is laterally convex at the cell, that is you can see here in this diagram also. Okay, this is convex. A negative plan or plan curvature indicates that it is laterally concave. Here you can see, right, it's a sort of like pushed inside and this is pushed outside. And then when it is like proper plane like this, a value of 0 is given to that surface, a linear surface. Then we have the profile curvature. So curvature of the surface in the direction of the steepest slope. Okay, this is more like a vertical plane kind of thing instead of the horizontal one. Okay, so it basically affects the flow velocity of water draining the surface and influence, and in turn which influences the erosion and the deposition. That is what we are considering here. So in this particular case, okay, so in this particular case, we are considering the vertical curvature, which is basically the curvature along the slope in the direction of the steepest descent. Okay, because however gentle it is, the flow of water will be not so intense, but the more steep it is, the more powerful the flow will be. That, and in turn we can also talk about the erosion and the deposition. In locations with convex profile curvature, as you can see here, the erosion will prevail, and in locations with concave curvature we will have deposition. Okay, so here it's sort of like the opposite, because earlier where you had convex surface you had the positive value, but here where you have the convex we have a negative value and a concave gives you a positive value. Why? Because where we consider erosion to be like losing something, like material is being lost, and deposition is that whatever that material is, it's getting deposited there. So that is why it is like given like this. Okay, so this profile curvature is parallel to the slope and indicates the direction of maximum slope. Because unlike this, the plan or planform curvature, that is not parallel to the slope, if you had seen the diagram. But this is parallel to the slope. It affects the acceleration and deceleration of flow across the surface, how fast or how slow that flow is. And as I said, a negative value indicates that the surface is upwardly convex and flow will be decelerated, because if it is convex, that flow will not be so intense, right? So it will be decelerated. A positive profile indicates that the surface is upwardly concave at that particular cell, and the flow will be accelerated because it's more easier. And value of 0, just like before, if you have a linear surface. Then finally we have the general, total or standard curvature. So the general curvature is also called as the total or standard curvature. It is the curvature of the surface itself and not the curvature of a line formed by the intersection of the surface with the plane. The general curvature can be positive or convex, indicating peaks, or negative or concave, indicating valleys, or zero, indicating flat surface or a saddle. So that is like quite straightforward. Like what, however that surface is, exactly this general, total or standard curvature represents. Unlike the plan or plan form one, where you had this intersection with the uh, surface and intersection of that with the plane. So that's not the case here, it's more direct. So wherever you have that elevation or the convex surface, we call it as positive. Wherever we have this negative part, that is the depressions that you have or valleys. So basically the standard curvature will combine both the profile curvature as well as the planform curvature. The profile curvature affects the acceleration and deceleration of flow, and therefore it influences the erosion and deposition. The plan curvature influences the convergence and divergence of a flow. So see, what we are exactly talking here is, in profile curvature, let's say this is a mountain or something like that, mountain and valley. So how like that flow is going to be like this, that is what we are talking about. And in plan curvature, if you take a look at this, you know, you can see these contour lines. So you can see how they are converging or diverging, and based on that, how the flow is converging or diverging. So considering both the plan and profile curvature, like when you consider both of them together, then it's easier for you to understand how the flow is happening across a surface. Like both you require, like you need to have an idea about the slope also in terms of the profile curvature. At the same time, you need to know how that elevation is varying based on the contours that you have in case of the plan form or plan curvature. So the application of curvature map, like why do we need curvature maps? So the application is, it is useful to understand the physical characteristics of a drainage basin. Drainage basin is basically for a river, right? So you can understand the erosion, runoff. So in order to understand such processes, we need curvature maps. In determination local factors of the dynamics of overland and intra-soil water, like you might have water over the surface or within the soil. So what all things does it influence, that kind of thing. Then curvature also influences the soil moisture, the pH, the thickness of soil horizons, organic matter, plant cover distribution, etc. The curvatures are an indicator of geological lineaments, ring structures, and can be used to determine fault morphology. So it's basically like you are assessing how that surface is uh, to you, like how we are seeing that, what kind of curves are there, and all those things. From that, you are able to understand the um, flow nature, the geological lineaments, and even the fault morphology. It can be used to map accumulation, transit, and dissipation zones of the land surface. This brings us to the problem part. So this is the first question. A DEM, which a digital elevation model, is a raster representation of a what kind of surface? We have the option as discrete, continuous, triangulated, and quadri. This is from the week 9 assignments. So I've straight away taken the questions because the solutions are already out. And I think you have already submitted it also. So yeah. What does a DEM like show tell you about? It's a raster representation of what kind of surface? So it's the answer is continuous, okay? So it's a raster representation of a continuous surface. The DEM could be generated through techniques such as photogrammetry, lidar, INSAR, land surveying, etc. Is this true or false? Okay, so the answer is true. Okay, so DEM can be generated using all of these techniques. Grid cell values can be what? Which of these following? It can be both positive and negative integer or even real floating numbers. It can be anything of these. But unlike like a grid cell values, this is fine. But the other one, the normal raster cell values, that is like either positive or negative. DEMs are commonly built using data collected using remote sensing techniques, but they may also be built from land surveying. Is this possible or not? Like, is it true or false? So the answer is true. Okay, it can be built from land surveying also, but largely we use the remote sensing techniques. There is no universal usage of the terms digital elevation model (DEM), digital terrain model (DTM), and digital surface model (DSM) in scientific literature. It can be used hand in hand, like it's not a universal usage. Is that true or false? The answer is true. So there is no universal usage, like people use all these three. Most of the terrain data providers, USGS, ERSDAC, CGIAR, ISRO, NRSA, use the term, like what do they use? Although like we don't have a universal usage, but still. So the answer is DEM. So although there is no universal usage, but even then these data providers, they mainly use it as DEM, digital elevation model. DEMs can be generated through a number of ways. However, most preferred method of generating DEMs is, actually I already said it before, but yeah, we can prepare DEMs through all these methods, but what is the common one? So it is remote sensing based. Okay, like we have multiple methods, but then this is the most preferred one. DEMs can also be generated using the following method: stereo pairs, thermal infrared data, radar data pairs, all of the above. Like, is it one of these or is it all of these? Okay, so it is all of the above. You can create DEMs using stereo pairs, thermal infrared data, or radar data pairs. Spatial interpolation techniques turns raw data into useful information by adding greater informative content and value, reveals patterns, trends, and anomalies that might otherwise be missed, provides a check on human intuition, and all of the above. Like we have discussed this before also, and I think last two sessions, I think some or the other question was there in the problems also. So, what essentially does spatial interpolation give you or do? So it does all of these. It turns raw data into useful information by adding content. It also reveals the patterns, trends, or anomalies that otherwise, like just by, without doing this, we might miss it. So that sort of helps. And it provides a check on human intuition. Like it uses logic rather than intuition. Functional surfaces can be used to represent which of these? Like terrestrial surfaces that depict the Earth's surface, statistical surfaces that describe a demographic, mathematical surfaces that are based on arithmetic expressions. Okay, so the answer is all of the above. So it represents the terrestrial surface, it represents the statistical surface, and it even represents the mathematical surface. Resolution may be best defined as which of the following: the accuracy and precision of the data, the overall quality of a data set, the smallest feature that can be mapped or measured, the smallest unit or measurement into which data can be disaggregated. So the answer is the smallest feature that can be mapped or measured. What is positional error? It's sort of very direct, but still. The answer is the error associated with displacement of the object from its true location. Okay, so positional error means the object is at a like one location, but while measuring, you measure it with including a displacement from its true position. So then you call it as positional error. A pixel with 1 meter spatial resolution covers an area of 1 meter square. How much area a cell with zero point 0.1 meter resolution in a DEM would cover? This is sort of direct, like you don't have to use much time in thinking. So it is 100 centimeter square. How? Like zero point 0.1 multiplied by zero point 0.1 will give you 0.01. So that is 0.01 meter square, which is basically 100 centimeter square. So that is all for today's session. Thank you for patiently listening to me, and I'm sorry with this scheduling problem. It's coming occasionally, not always, but yeah. Okay, so thank you so much.